Welcome everybody to the Johnson Matthey Platinum Group Metals Conference, Critical to the Future of Sustainable Technology. So what is the role of PGMs in the future technologies, or those technologies that are going to allow us to have a beautiful, sustainable and successful future as human beings on our wonderful planet? My name is Dr. Sarah Gordon. Now, before we get started, or basically the bit that you have all been waiting for, because of course this is a conference, and Emma, I'm going to invite you to maybe say some words against this particular slide, because of course this is a Johnson Matthey conference. There is a little bit of a legal disclaimer we need to flash up at the beginning in front of you. We will put this into chat as well if any of you want to read this in detail. Emma, do you have any words of introduction?
One of the key points that came up this morning was the question of mineral intensity. I would say it refers to the amount of critical material stuff you need per unit of technology, like per car or per gigawatt hour. And to quote the World Bank report on the mineral intensity of the clean energy transition, manufacturing solar panels, wind turbines, batteries, and I'm going to insert fuel cells, electrolysers, and the hydrogen and electricity infrastructures here, will shape the supply and demand for critical minerals for the foreseeable future. In the course of the conference, we've discussed supply and demand of PGMs extensively. Rhodium and palladium in session 2, which we're anticipating will go into surplus as the energy transition proceeds, and platinum earlier today, where the question was whether there will be enough to use in fuel cells, to which the answer was yes. In our first talk, therefore, this afternoon, JM's Mark Clapp is going to address the same question for iridium and electrolysers. How is there going to be enough iridium to ensure that hydrogen can make its critical contribution to the energy transition?
So Mark, if you would like to start sharing your screen and your slides, so we make sure that we can see what it is that you're going to present to us. I will now invite everyone, please put your hands together for the fantastic Mark Clapp. Thank you very much, everybody. Off you go, Mark.
Thank you very much for the introduction and for the chance to speak. So yeah, I'm Mark Clapp, and today I'll be speaking about green hydrogen via PEM, or proton exchange membrane electrolysis, and more specifically, whether and how we can avoid iridium supply limitations. And I think this is a really interesting and important topic because there's a lot of attention and a lot of investment into green hydrogen, and more specifically PEM electrolysis at the moment. But of course, the technology relies on iridium, which is, as we know, a scarce metal. So it's very important to have an in-depth and realistic assessment of how much iridium will this industry need. So just a quick run through of the agenda. I'll start off by just quickly giving an overview of the hydrogen economy and why it's important for decarbonising the world economy. Then I'll go on to trying to answer whether iridium availability will limit the rollout of PEM water electrolysis across the world. And then thirdly, I'll try and lay out some ways of how we can improve iridium utilization in our PEM electrolyser CCMs to hopefully avoid that limitation. So the hydrogen economy so the key thing about the hydrogen economy for me is that it can decarbonize so-called hard-to-abate sectors. So these are sectors that can't be very easily directly electrified, either via connecting to the grid or to batteries. So the broad idea behind the hydrogen economy is that you've hopefully got renewable electricity sources going in to produce hydrogen, green hydrogen, which can then be used to decarbonize things like heavy-duty transport, shipping. It can be combined with carbon dioxide and then carbon monoxide in the Fischer-Tropsch process to make synthetic fuels. It can be used to make green ammonia, decarbonize steel production and concrete production, and also perhaps for heating or grid balancing. In terms of hydrogen generation, there are sort of 4 electrochemical ways of producing the power producing hydrogen from electricity. These are proton exchange membrane electrolysis, PEM, which will be the focus of this talk. You've also got alkaline electrolyte membrane, liquid alkaline, and solid oxide electrolysis cell. I'll be focusing on PEM electrolysis because that is the most promising in terms of connecting to renewable energy sources and is receiving probably the most investment out of those at the moment. So why do we use iridium oxide, which is a very scarce, or iridium is a very scarce and expensive metal in PEM electrolysis? Well, to try and answer that, I'll first run through what a PEM electrolyser looks like if you zoom in on it, kind of thing. So here we've got the PEM, so the proton exchange membrane, which is sandwiched by two catalyst layers. On the anode side, you've got an iridium oxide catalyst, and on the cathode side, you have a platinum catalyst. The purpose of the iridium catalyst is to split water into oxygen and protons and electrons. These protons, or H+ ions, then transport across the membrane to the cathode side, where they are reduced, electrochemically reduced to hydrogen gas. So that's where you're evolving your hydrogen gas off. So the heart of this technology really is the catalyst-coated membrane, or CCM, of which you can see an SEM, or electron microscopy cross-section image here. So you've got your membrane and you've got iridium and platinum at either cathode. Now, why do we use iridium on the anode? Well, basically the rate-limiting reaction in producing hydrogen in this way is the oxygen evolution reaction. So this is a kinetically sluggish four-electron reaction. So it's very important that we are able to catalyze this very efficiently. So we need a very active catalyst, but not only that, this catalyst will also be operating at voltages up to 1.6 volts, which is a very oxidizing voltage for most materials, most elements. So we also need something that's very stable over the lifetime of an electrolyzer. So basically it boils down to iridium. It happens to be the best balance of activity and stability for the oxygen evolution reaction under these operating conditions. The problem is that global supply of iridium is only 7 to 8 tons, more or less, give or take. And there is not much scope for this to increase significantly because iridium is a byproduct of mining for other precious metals like platinum and palladium. Therefore, it's a possible limitation for the rollout of the PEM industry, and a significant concern for policymakers around the world. And I think it's important to tackle this question because policy bodies have been putting figures out there for how much iridium might be required, and some of them are just way off and far too high, really. So that was one of the motivations behind this piece of work, to try and go a bit more in depth and do some modeling as to how much iridium might we need. Now, to answer that, first we need to lay out or model how much PEM water electrolysis capacity we will need. So the International Energy Agency every year publishes scenarios as to how the carbon emissions of the world will change going forwards. And green hydrogen is a key part of these scenarios. So the announced pledges scenario relies on companies and countries meeting all of their pledges and targets that I've set out so far. That would limit global warming to 1.7 degrees Celsius. The net zero emissions by 2050 scenario, which does what it says on the tin pretty much, would limit temperatures to 1.5 Celsius. I would add that the world is comfortably on course to miss a 1.5 Celsius warming by the end of the century. So the net zero emission scenario is very ambitious. So with these scenarios, the International Energy Agency publishes mass of hydrogen produced per year from green electrolytic method sources. So a bit of work is necessary to convert this into a PEM water electrolysis capacity. So firstly, we need to take into account of the PEM market share. As I mentioned on my second slide, PEM won't be the only technology producing green hydrogen. There will be others, but according to an estimate by the German government, it should make up about 40% of the market going forwards. We also need to take into account sort of the efficiency of electrolyzing water in a PEM water electrolyzer. So that's in kilowatt hours per kilo of hydrogen. Based on the United States Department of Energy's estimates, that they think that will decrease from today's 53 to 45 kilowatt hours per kilo by 2050. We then need some unit conversions and also need to take account of the load factor. So of course, if you're connecting your PEM electrolyzer to renewable energy, that's an intermittent source of electricity. So it won't be on all of the time. So the load factor takes account of that, and the load factor of 0.6 seems to be a sensible estimate for what an electrolyzer connected to perhaps a large wind farm or solar farm would produce. So if we do that calculation, we can get these curves shown here. So we've got installed capacity on the y-axis and just years going forwards on the x-axis. And in green, we have the APS scenario, which is less ambitious, and the more ambitious NZE scenario in red. And I've also included an estimate or a projection from the Hydrogen Council, which is, well, it starts growing off slower, but is even more ambitious than the IEA scenarios by 2050. And the takeaway is that we will need anything between 600 gigawatts to well over a terawatt of installed capacity by 2050. Considering that today's installed capacity is probably under 1 gigawatt, this is quite a challenge going forwards, but the one that we will hopefully be able to meet. Sorry, just gonna find my mouse. There we go. So I've laid out how much capacity we might need. Now to address how much iridium we might need, we need to look at the efficiency with which this technology uses iridium. How much iridium does it need? So we can define iridium utilization in terms of an iridium specific power density, which is the milligrams of iridium you need per watt of electricity that goes towards hydrogen production. So basically, mass of iridium per watt of power used. And this iridium-specific power density needs to be reduced to make the iridium utilization more efficient. So basically, at a given cell operating voltage, so whatever voltage your electrolyzer is operating at, the current that you produce, which is going towards hydrogen production, per mass of iridium needs to go up. Now we've got various organizations setting these sorts of targets, which if you do a bit of normalization of the units, you can plot in this sort of graph that I've got here. So we've got targets from the US Department of Energy, the EU, IRENA, and the German and Japanese governments. So we've got this iridium-specific power density on the y-axis, years going forwards on the x-axis, and we see that all of them project quite a steep and dramatic decrease in iridium improvement, basically, in iridium utilization going forwards. When I was plotting this, I noticed that the American and German government's projections were more ambitious than the EU, Japanese government, and IRENA. So I categorized them according to conservative and optimistic scenarios, so in blue and red going forward. So now we've got two scenarios in terms of how the iridium utilization of this technology might vary in the future. And the bottom line is that in both cases, we need a more or less tenfold improvement in iridium-specific power density from today to 2050. So going from, in the conservative scenario, about 1 milligram per watt to about 0.1 by 2050, and 0.5 to 0.05 by 2050 for the optimistic scenario. So that's the research challenge, really. That's where R&D needs to step up and do the work to reduce the use of iridium in this technology. So now we have the capacity that we'll need, we have the iridium utilization and how that will evolve with time. So we can start calculating, estimating how much iridium the PEM industry will need in the future. So the total demand of iridium will, in year I, is the sum of the new capacity that you're installing in year I, and whatever capacity that you're having to replace in year I, which is coming to its end of life in that year. And if you multiply by the iridium power density, that gives you a mass of iridium demand that year. But of course, I'm really interested here in how much primary iridium we will need. So by primary iridium, I mean the amount that is coming out of that world supply of 7 to 8 tons that is, mined that year. To calculate that, we first need to take account of the amount of recycled iridium that is circulating within the PEM electrolysis sector. So any end-of-life electrolyzers can be recycled and the iridium put back into the industry. So that can be calculated by the total iridium used to install electrolyzers tau years ago. So it's now coming to its end of lifetime, multiplied by an efficiency of recycling factor. And that gives us the recycled iridium in year I. And then finally, we can put those together, and by subtracting the recycled iridium from the total, we can calculate the amount of primary iridium needed in year I for the PEM industry. So this poses the question: how much of this primary iridium do we think is realistic? Okay, so we've got more or less a 7.5 ton per year supply. And we, Johnson Matthey, think that 20% or 1.5 tons per year is a realistic figure. That's taking into account particularly demand reduction in spark plugs and potentially in other uses of iridium as well. So 20%, 1.5 tons per year. That's kind of a threshold that we're working with here. So if we put all of this together, we can actually start to model how the iridium demand will change going forwards in time. So here we've got the IEA announced pledges scenario, so the less ambitious scenario for both the conservative and the optimistic technological development scenarios. So conservative and optimistic in terms of how quickly the iridium utilization will fall with time going forwards. Just to explain the axes, on this y-axis, we've got the annual mass of iridium needed. And the key line to pay attention to here is the solid black line, which is the primary iridium required annually. The dashed one is the recycled, and the dotted one is the total iridium that year. And on the right-hand y-axis, we've got a bar chart showing how the iridium accumulates in the PEM sector. Because, of course, as we recycle it, we need less and less new input going forwards in time. So in the conservative scenario for the APS, we get a fairly large peak around 2025 of 4.7 tons per year, which is comfortably above this 20% dashed line here in red. That's your 1.5 tons per year. However, if you assume the optimistic technological development scenario, then actually that primary iridium supply stays below the 20% line throughout all the way through to 2050. So this is really showing how technology and R&D development can really empower this sector and help it avoid any iridium limitations. Now, the story is the figures look similar for the IEA net zero emissions by 2050 scenario, except that they're bigger because it is a more challenging, more aggressive scenario in terms of PEM capacity. So here we get the iridium demand peaking at 13 tons per year in just before 2030, which is pretty unrealistic. However, again, if that pace of technological development follows the optimistic scenario, then it only rises to 2.5 tons per year and actually dips back below the 20% level by 2035. So this perhaps represents a demand level that the iridium market can absorb. So the headline, the takeaway is that both scenarios, the NZE and the APS, are possible if the technology follows this optimistic scenario of improvement. And again, I should emphasize that the IEA NZE scenario is very ambitious, and the world, unfortunately, is not on target to meet that. So on the previous slide, I examined, given a certain capacity projection, how much iridium will we need? But to me, almost more interesting is to think about, well, okay, if you've got X amount of iridium each year to play with, what sort of capacities could you achieve by 2050? So that's what we've done here. So we've got PEM capacity on the y-axis, time going forwards on the x-axis, and just looking at the orange thick line, that's the 20%, 1.5 tons per year level. In the conservative scenario, that's almost enough to reach the IEA APS, match the IEA APS scenario's capacity. However, and in the optimistic scenario, it's actually dramatically better. So it actually beats the IEA NZE scenario by 2050 and actually reaches 1.3 terawatts of installed capacity by 2050. Now, this feels like quite a significant result, because this is saying that if the R&D improves significantly enough and fast enough, and we've got 20% of the iridium supply annually to play with, and we do recycling, then we can actually exceed the NZE scenario, which is a promising and encouraging result to have. Okay, so far I've spoken about, so I've laid out, how much iridium might we need, and also equally what sort of capacities could we reach. So now I want to talk a little bit about how we can enable ourselves to match that optimistic scenario of technological development, and how we can reduce our iridium utilization. So without getting too technical in the electrochemistry, here we've got what's called the polarization curve of an electrolyser. So we've got current on the x-axis, which is like your hydrogen output. And we've got voltage on the y-axis, which is like your energy input. So what we're trying to do is, for a given voltage input, we want to get as much current as possible. So we're trying to push this dashed black line down as much as possible, while keeping the amount of iridium, while lowering the amount of iridium used in that electrolyser. So here in these different colors, I've got the breakdown of all the voltage losses in an electrolyser. So in blue, I've got the intrinsic loss for catalyzing that sluggish oxygen evolution reaction. This is what our iridium oxide catalyst can affect. And then in sort of purpley color, I've got the membrane resistance, which is part of the cell resistance, which is the other significant contributor to your energy losses. So there are three levers we can use to really improve iridium utilization. We can reduce this cell resistance, primarily by reducing the membrane resistance by just going to thinner membranes. We can decrease the iridium loading while maintaining the same sort of current and voltage performance. And we can also increase the intrinsic activity of this iridium oxide catalyst so that our blue band here is squeezed down and gets smaller. And out of these 2 and 3, levers 2 and 3 are the ones to do with the iridium oxide catalyst, which is what my last 2 slides will be on. However, first, just very quickly here, bit of a complicated slide, but what it's trying to do is lay out a future scenario in terms of how these 3 levers for improving iridium utilization might vary in a realistic way to achieve that optimistic scenario, which would allow us to have potentially 1.3 terawatts of capacity by 2050. So as you can see, your membrane thickness has to go from 125 microns to 50, which, by the way, is similar to what fuel cells have. Fuel cells have gone to thinner than that as well. So there is a precedent there. The loading needs to come down by over a factor of 10. And the intrinsic activity also needs to increase by over a factor of 10. But the good thing about mapping this out like this is that none of these are completely unrealistic. So all of these feel achievable from a research point of view, which is very good news. So to finish off this last bit of my talk, I'll discuss the different types of iridium oxide catalysts that we might use to improve iridium utilization using levers 2 and 3. So very quickly, for a good iridium oxide catalyst, it has to be active for the OER. It has to be able to form laterally conductive catalyst layers at low loading. So once you go to very low loadings, you've actually got so little iridium, such a small amount, that your catalyst layer actually starts becoming disconnected because it's just not thick enough to form a good structure. You need good stability against dissolution to give you that lifetime, and you also need a scalable synthetic method. If you look in the literature, the catalysts, there's a lot of research into this, a lot of research papers, and the catalysts that they are developing can broadly speaking be categorized into 5 categories. So you've got a nanoparticulate iridium oxide, which is just a collection of pure iridium oxide nanoparticles. Then you can decorate these nanoparticles on some sort of high surface area support. That's then your supported nanoparticles. You can have a core shell structure, so where you have iridium oxide as the shell and the core of the particle is another material. You can have a mixed oxide, and you can also have an extended surface structure where you're trying to get that continuous connectivity of iridium oxide rather than particle-particle junctions like here. Now, when the first COVID lockdown struck in the UK, I was at home for about 2 months, and I did a lot of reading of the literature, which resulted in these graphs. So here I've collated basically all the different academic publications that do CCM testing, so electrolyser testing, with the different type of catalysts outlined on the slide before. So basically here, the better catalysts are towards the top left-hand corner of the graph. It's probably easier to actually look at figure B here. What I've done here is just average their performances for the different categories. And what we see is for iridium-specific power density, which of course we're trying to decrease, the nanoparticulate catalysts don't really get much beyond today's level of performance. That's because once you go to low loadings with these nanoparticulate catalysts, you actually start forming that disconnected catalyst layer that I spoke about on the previous slide, which then results in large resistances. For supported nanoparticles and extended surface structures, the picture is much rosier. So those are actually able to form good layers at even very low loadings because you're bulking it out with a different material. and the extended surface structures just have really good two-dimensional conductivity. And the mixed oxides come somewhere in between the two, but it's a bit early to say because there weren't many published data sets for those. So the outcome of this is that extended surface structure and supported nanoparticulate catalysts seem to be the most promising ways forwards to reduce iridium loading to that 2050 optimistic target. With that, I'll wrap up just very quickly. This work is, there's a paper associated with this work with the reference on the screen here. So if anyone's interested in finding out more or looking in depth about the sensitivity studies and all the calculations, please do. And with that, thank you very much for your attention, and I'm open to any questions.
Mark, thank you so much for that. In line with all the other talks that we've had, that was truly brilliant. So thank you very much. Everyone, round of applause for the fantastic Mark Clapp. Excellence.